So this is a brief introduction to integrating parametric functions. As a reminder, for our parametric function, it's where we're given x as some function in terms of t and y as some function in terms of t. Now, we're going to modify looking at the area under the curve and the volume of revolution equations a little bit. Now, before we looked to see that if we've got the area under the curve and we're given our limits in terms of x, we can integrate the function with respect to x. That would get us the area. Well, if we're given parametric equations, typically our limits are going to be given in terms of t, so it's much easier to use the parametric equations to help us. So instead, we're going to integrate between our two t limits of y times dx by dt with respect to t. Because the dx by dt and the dt's will cancel, which simplifies us back to the y, integrating y with respect to x, but this allows us to use our variable t for our limits. Alternatively, if we were given our limits in terms of y and we've got x dy, so we can reverse the process again, our limits are in terms of t, where we can have x times dy by dt again, the dt's cancel, simplifies the problem. Taking that to the volume of revolution then, so we've got our expression from before, which is that the volume is equal to pi times the integral of y squared with respect to x between our two x limits there. So again, it's a slight modification. So if our limits are given in terms of the parametric variable t, we've got pi between the limits of t1 and t2 of y squared times dx by dt, and integrating with respect to t, again the dt's cancel, leaving you pi, the integral of y squared dx. And a similar idea then, where we had pi of the integral of x squared with respect to y when our limits were given in y, so we've got pi, the integral between our variable t of x squared dy by dt.